Then what? Well then, check it out, AB minus AC, which is of course equal to A times B minus C, is equal to 0, right? But what? But thus what? Thus B minus C must be equal to 0, as A is not equal to 0, right? So you have the product of two. This is a product in integral domain R, right? You have the product of two things in the integral domain. One of them's non-zero. Process of elimination. The other one has to be 0, otherwise we'd have zero divisor, which is forbidden, right? So it must mean that B minus C is equal to 0, which tells us what? B is equal to C, right? This is not true when you don't have an integral domain, right? And so like Z mod a composite is a nice source of examples of how things break down outside an integral domain. Like let's try this out. Let's see if you can come up with sort of a counter example how this doesn't work out. And see, let's say Z10, you know? You could have something like what? 4 times 5 is equal to, let's see here, I don't know, 8 times 5, right? Those are both equal to 0. Right? Yeah. A is not equal to 0. So my 5 is like my A, right? This does not imply 4 equals to 8. I mean, 4 is not equal to 8 in Z10. The reason this is happening to us is because Z10 is not an integral domain. It doesn't have the cancellation property. All right? But does the cancellation property mean that there's an inverse? Right? Does it mean that there's cancellation? Like, warning, be careful, right? If you have something like x squared plus 1 times x plus 3 equals to, like f of x times x plus 3, that does, in let's say in zx, right? Then because zx is an integral domain, that does imply that, x squared plus 1 is equal to f of x, right? But that's not because I'm multiplying by x plus 3 inverse, right? X plus 3 inverse, by the way, x plus 3 inverse does not exist in Z adjoin x, right? If there is an inverse to x plus 3, it's not in Z. It's not a polynomial with coefficients in Z. It's somewhere else. Okay? Just a cautionary tale. Now, that leads us to the following definition. A commutative ring with unity, right, in which every non-zero element is a unit is called a what? A field. Very good. All right. So is a field an integral domain?
Yeah.
Why?
Because everything is a unit, and therefore zero divisors.
Zero divisors can't be units. Oh, that's true. Because of the thing we did earlier today, very good, yeah. Because of that homework problem I solved in class. Oops. But of course, there is, that's a good way to argue. Let's see here. Certainly we have the cancellation property, right? Because if we have, AB equals to AC for A not equal to 0 with, in a field, then A inverse AB is equal to A inverse AC, which implies, of course, that B is equal to C, because A inverse A is the identity, right? But notice, again, the cancellation property doesn't have to be based on multiplication by inverse. In integral domain, we kind of skip past that. Sneaky. Theorem, and the proof of this theorem seems too easy, but it's one of the beautiful proofs. Each finite integral domain is a field. All right, so let's let D be finite integral domain, all right? So it's already, by assumption, a commutative ring, right? With identity. That's all built into the definition of integral domain, which I have sadly just erased. Okay? So the only thing that has to be checked is what? Every non-zero thing has an inverse, right? That's what we have to check. So let A be an element of D, right? And with A not equal to 0. Okay? I said if A equals 1, then A inverse is equal to 1, so great. Otherwise, A is not equal to 1, right? Hence, consider the following list. So we can look at A squared, A cubed, A to the fourth, ... right? This is a subset of D, right? And because D is finite, eventually we can erase that subset. We have to, well, it doesn't ever have to get 0, right? But it has to, well, what has to happen, actually, is it doesn't have to be all of D, right? But it eventually has to loop back on itself. Otherwise, we'd have an infinite subset of a set, right? So it has to, eventually, this has to circle back on itself. Otherwise, we'd have an infinite subset of a finite set, which is absurd. Right? So if you think about that for a second, finite implies that A to the I is equal to A to the J for some, for some I and J. But what does that say? That says that A to the I minus J, right, is equal to 1, which of course says that A inverse is equal to A to the I minus J minus 1, So in other words, we have shown that every non-zero element of D is a unit, therefore it's a field. So finite integral domains are necessarily fields. How about infinite integral domains? Are they automatically fields?
Well, yeah, if they're all units.
So again, an infinite integral domain is just a commutative ring with identity, which has no zero divisors. So
I guess you could have one that doesn't have everything making it a unit.
So yeah, so the example to go with is just the integers, right? So the integers, this is an infinite integral domain, right? But 2 inverse is a half is not an element of Z, right? So therefore, Z not a field.
It's not an element.
Right. Thank you. Yeah, no, you're correcting me. I appreciate it. So I won't even write this one down. Corollary, if P is prime, Z mod P is a field. All right, I'll just, example, Z mod P is a field because, in fact, we already know this, right? We've studied this in some depth. UP is, what is it? It's got everything in it, up to P minus 1, right? That is all the non-zero things. That is literally the list of ZP with removing 0 from it, you know? Like, yes, Z mod of prime is a field. There are other fields, though, that are more interesting that we haven't seen yet. Example 35. Check this one out. Z mod 3 adjoin I. So what we're looking at is A plus BI, such that A and B are in Z3. So just to like list it out explicitly, you got yourself your 0, your 1, your 2, your I, 1 plus I, 2 plus I, 2I, 1 plus 2I, 2 plus 2I, right? And I won't bore you with the calculation, but you can prove that this is in fact a integral domain. All right, I have the calculation on page 127. It shows that this is an integral domain. All right. So what does that mean? So short calculation. Shows no zero divisors. Therefore, Z is integral domain. So that means then that it's finite. It's a finite integral domain, right? So it's a field. Is a field with how many elements? With 9 elements. That's something that we couldn't have created as Z mod P, right? Like Z9 is not a field because 9 is composite. So this is something new. Example 36, I'll just mention, I won't get into the details, but if you look at Q adjoin the square root of 2, this, in other words, A plus B root 2, A and B rational numbers, you can prove that that is a field. All right, this is an example of what's called an extension field. It's the field of rational numbers adjoining one more thing, the square root of 2 actually. So.
Does that thing have to also be like maybe anything?
Well, we'll talk about that. Certainly if you adjoin something that's already in the field, you just get the field again.
Yeah.
Can it be anything? And if you do adjoin something, what are its properties? Those are interesting questions that we seek to answer. So final storyline for today, we want to talk about characteristic. All right, what is a characteristic of a ring? Have you guys ever heard the terminology characteristic 0? Wondered what that meant? What does it mean to have characteristic 0? So, definition, the characteristic of ring R is smallest positive n such that nx equals to 0 for all x in R. All right. We say char R equals to n in this case. All right. Otherwise, if no such n exists, then the characteristic of R is said to be 0. Now, you might expect it to be infinity, but we say 0. Okay? And then theorem. So this isn't how I remember characteristic. This theorem is actually how I remember it. If R has unity 1, all right, then R has characteristic 0 if 1 has infinite order, and if 1 has order n, then char R is equal to n. Yeah, the proof is essentially just this calculation, all right? So I'll just focus on the n times x, right? What's that mean? This is x plus x plus x plus x how many times? Right, n times, n summands. But you can factor 1 out of each one of those, right? And by the distributive property, you got 1 plus 1, right? And again, there's also n summands of that. So what's 1 plus 1 plus 1 plus 1 n full times? Well, that's n. So this is nx. Well, I'm coming back full circle, aren't I? I was about to go back where I started. That would be dumb. But the point is that this is n times 1, right? Times x. So here's the argument. If you know that, so when I say that the order, 1 has order n, we're talking about additive order. Like multiplicative order of 1 is dumb. It's 1, it's the unity. Multiplicative entity. So the additive order of 1, if it's n, that means n times 1 is 0. And nothing before it's 0, right? So if n times 1 is 0, and that's the smallest n, which is 0, which gives you n times 1 being 0, then that makes nx equal to 0 for all x, which says it has characteristic n. Now, if 1, and by essentially the same calculation, if 1 has infinite order because of the same link, if you somehow had nx equal to 0 for all x, well, that would imply that 1 had an order which was an infinite. Anyway, so theorem. Characteristic of R where R is integral domain is either 0 or a prime. So if 1, I say if 1 has infinite order, then the characteristic of R is 0, so we're done. All right. Suppose that n times 1 equals to 0, we're you know, in the additive sense. So suppose, let's look at the additive case. So suppose the order of 1 is equal to n, so n times 1 equals to 0, right? And suppose n is equal to s times t, right? For some 1 less than or equal to s comma t, less than or equal to n, right? And then, well, we can calculate 0 is n times 1, right? but that's equal to st times 1, which, by the way, we can rewrite as s times 1, t times 1, right? But neither of those can be 0. Well, let's see here. The only way, they can't both be 0 for like smaller s and t. The point is either one of s or t has to be n, otherwise it contradicts the order of 1 being n, because you'd have a smaller order which goes to 0 on the basis of this theorem. So there it is in a nutshell. The characteristic of an integral domain is either 0 or prime. Now this is in good agreement with what we already know, right? What's the characteristic of ZP? So yeah, this is equal to P. For example, in Z3, 1 plus 1 plus 1 is 0, right? And that's the first time that happens. What are the rings with characteristic 0? Well, they're the ones we are most familiar with. Integers have characteristic 0. Q, Z, the reals, the complexes, these are all characteristic 0. Almost my entire mathematical life is spent in characteristic 0. The only place I ever find myself talking about characteristic not equal to 0 is in a course like this, where we're studying abstract algebra. So such is the nature of my existence, but not everybody. Some people spend most of their existence in characteristic 2. Those are computer scientists, you know, for the most part. Anyway, that's it, guys. So, thank you for bearing with me.